JWST.
Sorry about that.
And what I hope to do, you know, at various times is bring you updates on the telescope and what's happening. And I thought today that I would talk about one of the things that JWST does, which is studying galaxies in the early universe. So we'll try to take a look at what that means. Why JWST? What is the early universe? And so as I talk along, if you have questions, you can put them in the chat. If you want to raise your hand, maybe I'll see it and maybe I'll not. I won't, but we'll also have time at the end, I hope. So remember that JWST was launched on Christmas Day a year ago, and it's important for me to point that out. The whole JWST mission isn't done yet. JWST will last at least a decade, hopefully two, maybe even more. And so I'm just talking about what we actually have discovered in the last 6 months or so, because it took it a while to get up and installed in commissioning. And what I'm really focused on is what we see at the very earliest moments of the universe that JWST can see, a few 100 million years after the Big Bang. So here's a picture, which has just actually been released in the last week or two, where you have an image from JWST covering a large area, which we will talk about. And then in that image, there are a couple of little cutouts here, where on the right-hand side, you see the images. So this is image of this little box number 1, this little box number 2, and this is what's in this box number 3. And it is believed that those galaxies our image of them are existing about 100 million years after the Big Bang. And I'll have to explain that, obviously. Okay, so first of all, early galaxies formed a long time ago. When we talk about early, we're referring to the time in the history of the universe, where the universe began about 13.8 billion years ago in an event that occurred everywhere in the universe 13.8 billion years ago, and that's what we call the Big Bang. And what and here is today, the modern universe. And in the meantime, 13.8 billion years of history has gone on. And one of the main things that JWST is supposed to do is help us learn about that history. And so what we're talking about is early times, not the very beginning, not after that, but this epoch around 100 to 500 million years after the Big Bang. And we want to know what happened then. Now, it's also important to point out that JWST really is a technical marvel. It cost a lot of money. It took a lot of time. But the real reason is that it uses technology that didn't exist 10 years ago even. And it was designed to replace 2 different of the NASA Great Observatories, as they were called when they were launched back in the late 70s and 80s and 90s. And the 2 are the Hubble Space Telescope, which you're probably familiar with, but another telescope called the Spitzer Space Telescope. And what you're seeing blinking back and forth here is the image from JWST and the image from Hubble of the same region of the sky. And what you're seeing is the JWST image, which is this one, has better resolution, angular resolution, which means the images are sharper. It also has a bigger mirror. It's 6.5 meters instead of 2.4 meters in diameter. So it collects more light, more photons, and therefore it allows us to see fainter objects in the same exposure time. Yeah. And the other thing is it operates with different sets of filters than Hubble does, so that Hubble observes mainly the same kinds of light that our eyes see, whereas JWST is designed to see the light that we call the infrared. So to remind you what that looks like, well, here's another picture of the Hubble and the James Webb without the blinking. And it's just to point out that JWST is the next generation Hubble. And so it better do a lot better than Hubble, and therefore we should also learn a lot more. The specialization in the infrared light can be depicted this way. So this is what we call the electromagnetic spectrum. There's a little part of it here which we call the visible part of the spectrum, and that's what our eyes are sensitive to. And we like to describe the different colors that we see. What makes light different, one kind to another, is the waves that make up the light have different wavelengths. So long distances between the waves, shorter, really short, going to incredibly short, going from the gamma and the X-rays to the ultraviolet. Then this is the part that our eyes can see. And then we have the infrared, the microwave, and the radio. And down here, you can see that Hubble operated in these wavelengths. Webb is designed to operate in these wavelengths, and Spitzer operated in these wavelengths, which overlap with Webb, and Hubble overlaps with Webb. But Webb is focused on that infrared part of the spectrum. So here's an image of what you see with standard night vision in the visible wavelengths. But in the infrared, you can actually see more features that don't show up in the visible part of the spectrum. And so this is what we want to target. We can target objects in particular that have cooler temperatures than you see with our eyes, because our eyes have evolved and developed because they are supposed to respond to sunlight.
Hotter temperatures have shorter wavelengths.
Hotter temperatures have shorter wavelengths. That's an important thing. We'll come back to that. So another thing to point out is we're going to take a look at a few images. The Webb can peer through and examine dust. Now we know that when you're looking through a piece of paper, you can't see anything behind it. Dust also obscures visible light behind it. So here are three images which we'll take a look at. These are actually, this is not JWST data because it was made to show why JWST was important before it was launched. Here's an image taken of a region of the sky in the visible light. Here's an image taken in the near infrared light. It's taken from the ground, but it's similar to what JWST would see. And here's an image that's taken with Spitzer, which is a region of the infrared light that JWST can see, but you can't see from the ground. And you see the images show different structures. This is the same image of the sky. And in particular, I want to point out that in this visible light image, there are regions that appear black. Whereas when you go to the infrared, you actually see in those same regions, you see bright glowing objects. And in this case, the reason is because there is dust in front of those glowing objects, which completely block out the visible light, but the infrared light gets through. And so stars embedded in or behind dust begin to be seen only when you go into the near infrared. When you go to the mid-infrared, which JWST also operates at, you actually see that dust glowing. And the stars and the dust both glow. And so you get a very different feeling for what this object is made up of when you compare this image to this image. And so in order to understand the sky, we have to understand what we're looking at. And here are just some regions. You don't see it at all. Here you see that there's something in there, and here you see all the stuff that's there, which in the other images appears black. Okay, so back to our JWST explores the early young universe. Again, what we're interested in is trying to understand what happened 100 million years after the Big Bang. And before JWST, we have not been able to observe that far back for a variety of reasons, which we're going to talk about now. Okay, So first of all, the reason that it's hard to find these galaxies is that they're not very prominent. So here's the image we took a look at before. Again, these are what are believed to be distant galaxies. Here's the whole image. They're not very bright, they're not very big, and they don't look like much. But they're very interesting, as you'll see, I hope, in the rest of the talk. So first of all, why are these galaxies interesting? Why do we care? First of all, light emitted from distant galaxies took a long time to reach us. Light travels at the speed of light, 186,000 miles or 300,000 kilometers per second. And it travels, what we're talking about is it's traveling for more than 13 billion years in order to reach us. So the nice thing about astronomy is that if we look at distant galaxies, we're actually seeing them as they existed billions of years ago. And we want to know, how was the universe different in the past? What was it made up of the same stuff as today? We also want to know, we know that the universe is much older than the sun is. And so we want to know what the universe was like before the sun existed. The universe in the past was smaller, galaxies were close together, and therefore the sun was formed 4.5 billion years ago when the universe was relatively mature. What we really want to know was what the young universe was like when it was hotter and denser, and also an important point which is important to our study of dust is that the early universe contained hydrogen and helium. It didn't contain carbon, nitrogen, and oxygen, the stuff required for life. And we want to understand how that affected what galaxies and stars were like in those days. Another reason that distant galaxies are interesting is that they should be able to tell us about those early epochs and how the universe was expanding at that time. This is a subject that I'm not really going to talk about today because it's beyond the scope of today's lecture. Maybe another time. So now let's ask the question, why do different galaxies look different? So here's the image of the Hubble Space Telescope, of the JWST. And almost all of the objects in this image that you see are galaxies. Galaxies contain, as my late colleague would say, billions and billions of stars, and they're very far away. Let me also point out that there are a few features in this image, which are stars in the foreground, which look like those pointy things because the light from them is so bright that it interferes with the telescope and causes that what we call a diffraction pattern. The stars don't really look like that. Just there's so much light they cause this pattern. The other objects, though, are almost all galaxies. So we have to ask some simple questions. First of all, why do some galaxies appear smaller and fainter than others? One reason is the galaxy is intrinsically small. And in fact, galaxies come in a variety of sizes and brightnesses. And so here's an example of one of the nearest galaxies to us, the Andromeda Galaxy, also known as Messier 31. It's at a distance from us of about 2.5 million light years. Million, not billion, million. So that's like almost next door. The light, however, traveled from Andromeda 2.5 million years to us in order for us to make this image. Andromeda is a bit bigger and brighter and more massive than the Milky Way. Notice also that what you're seeing here in this image is starlight. Stars also contain gas and dust and dark matter, but this image doesn't convey any information about those, or very little information about those. But let's also point out that in this image, there are some other galaxies as well. And those are these two, the one here, Messier 32, and this one, NGC 205. They are at the same distance as Andromeda, but they appear fainter and smaller because they really are intrinsically smaller in physical size and less luminous. And we call those dwarf galaxies. So we have to understand that galaxies come in a bunch of different varieties. Some of them are bigger than others, some of them are brighter than others. And we can't just look at a galaxy and know exactly how far away it is. Another reason that galaxies appear smaller and fainter is not just because they are dwarf galaxies, but a small galaxy might also be a distant galaxy. And that's because if you take a light bulb and put it further away from you, it appears fainter. And if you take a ruler and you look at it from a large distance, it appears smaller. It has a smaller angular size. So the precise amount of becoming smaller and fainter depends on the geometry of the universe. And as we're going to see, there are different effects that can cause galaxies to look different. Galaxies have different colors, and you can see that in this image. Some of them appear, relatively speaking, blue. Here are some blue things. Bluer, bluish, bluish, bluish. And some of them appear redder, 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 redder. I'm not saying blue or red. I mean relatively red or relatively blue. And the answer to why galaxies have different colors is complicated. And here's just a montage of relatively nearby galaxies, which we can look up close. And you see that they have different shapes, and they also have different colors. And it's been a subject for 100 years, several hundred years, more than 100 years, 150 years, why some of these objects appear red, and some appear blue, and some appear smooth, and some appear to have spiral arms. But do note that most of the smoother galaxies have a tendency to be redder, and most of the galaxies which have spiral arms have a tendency to be bluer. So we understand that. Again, what you're seeing in a visible light image is the starlight. If a galaxy contains no stars that are massive and young, then the galaxy will appear red. That's because young massive stars are blue and hotter, older stars are red and cooler, and low mass stars of any age are always red and cool. So if a galaxy has a lot of young massive stars, it will look bluer than a galaxy that does not have any of those stars. If you see that a galaxy is red, it doesn't tell you anything about the young stars that are massive. Another reason a galaxy can appear red is that a galaxy may contain a lot of dust in its interstellar medium. It turns out, we talked a little bit about the dust, and here we have 3 images of the same galaxy, one taken in the optical, one taken by JWST, and then that's this one. And then this is a composite of the 2. And I just really want to point out the fact that in the optical image, you don't really see this region very much. This is designed to show us, it shows up in the composite image. Here it shows up. The dust in between the stars can absorb and scatter the blue light more than the red light, and you won't even see the object when you look at the visible wavelengths. The way this image has been made also is important to us. You know, our eyes would not see this image, anything, if we looked in this wavelength range, because our eyes aren't set up. So we also have to keep in mind that when you see an image that comes from a space telescope or a radio telescope, someone has made up the color palette to try to convey some information. So now, why do some galaxies appear redder? The galaxy may have no stars that are massive and young. It may contain a lot of dust, or it also may be very distant. And that's what's really important to us. And the reason for that is that the expansion of the universe, what Hubble discovered was the universe is expanding. It's getting bigger over time. And the more distant galaxies are moving away from us faster than the nearer galaxies. The expansion of the universe causes the light from those galaxies, the light waves, to be stretched out to longer wavelengths. So they are shifted to longer or redder wavelengths. So again, that's the amount of the shift in the light is proportional to the distance to the galaxy. So the bigger the shift, the more distant the galaxy. What that means, and here's another image from JWST and a galaxy which is believed to be very distant, a galaxy that would look blue if we could observe it close to us in the modern universe. It will appear red if we observe it from very far away. A galaxy that looks red nearby will just appear even redder. So keep that in mind. Both the blue galaxies and the red galaxies look redder as viewed from far away. So if we want to find distant galaxies, what we want to do is look at these tiny red galaxies that you see in the image. The images suggest that this galaxy might be distant, but we have to prove that it's distant because it's complicated. You also have the dust problem. So some galaxies appear redder than others because it depends on whether they have young massive stars, it depends on how much dust they have, and it depends on how far away they are. And of course, some galaxies could be affected by all three of these. And so our problem, and the reason that JWST is going to be so important because of all of JWST's technological advances, is because it's going to allow us to unambiguously interpret the color. So here's this image that I keep showing you, which is the targeted image, one of the first released images from Hubble that were released last June or July. It was the target of exposure by JWST specifically because it's already been studied by Hubble and by radio telescopes, X-ray telescopes. And what it contains is actually a cluster of galaxies containing thousands of galaxies that lies about 5 billion light years away from us. 5 billion is kind of middle age universe. It's actually what we call cosmic noon. The light we're seeing here was emitted in the epoch when the sun was formed in the universe, in the history of the universe. The light has traveled about 5 billion years to reach us. Here's a close-up of the image to show a couple of things. First of all, the image that you see here contains thousands and thousands of galaxies. Some of them are nearby, some of them are 3 billion light years away. This cluster of galaxies, all these galaxies that you hear, especially the ones that you see in white, white is kind of halfway between red and blue, okay? The colors mix together and you see white light, or what we call white light. And these galaxies, the light left 5 billion years ago. But what we're really interested in is these little teeny tiny things that you can see. Are they tiny red galaxies nearby, or are they big galaxies that are just really, really far away? And that's why Hubble hasn't finished the problem, because it's not that easy to know the difference. Now, an important thing and a reason why this image was targeted as being one of the first images is you also notice in this image, there are all these streaks across. And what those are a phenomenon that we call gravitational lensing. And gravitational lensing occurs when you have a foreground object like this cluster of galaxies, and then behind it, there is a small object, and the light from that object travels towards us and goes through the cluster of galaxies, which contains a lot of mass. And the mass, the gravitational mass of the foreground object, bends the light from the background object the same way that an optical lens can be used to magnify and make brighter a distant, small, faint-looking object. what you get when you look through a small telescope or a pair of binoculars. It's the same phenomenon, except it occurs because of mass and gravitational lensing, not an optical lens and optical lensing. And so here's the idea of that. We have a massive cluster of galaxies. There's a very distant object, and the light from that distant object travels towards us. And depending upon where we are, where our eye is, if it's a little below or a little above relative to this object, we see images that are caused by the gravitational mass of this foreground cluster. So a massive cluster acts as a foreground gravitational lens to brighten, magnify, and distort the images of the galaxy located in the background. It's also often true that there's not just one object in the background. There could be many different galaxies in the background that are affected by this foreground cluster of galaxies. And so the detailed pattern of the arcs that we see in the image here, the detailed pattern, is caused by the fact that we have a mass distribution in the foreground, which isn't just a simple lens. It's got all these big galaxies in it. It's like a lumpy lens, a funny house lens. And also there isn't just one galaxy behind it. There are a bunch of them, and they're at different distances. And so we get this very complicated pattern, but we can try and understand what it is that's causing these various streaks. They are images of background galaxies. The important point about this from our perspective is that gravitational lenses actually act like telescopes. They cause the background object to appear brighter and bigger. And therefore, if a galaxy is lensed by a foreground massive object, it shows up more easily. So a strategy, if you want to find small little objects in the background, is to look where you know there's a gravitation lens, because the background objects will be made brighter than they would be if they didn't have that lensing phenomenon going on. And so the next thing that JWST is also going to be able to let us do, and here's an image from Webb, and here are a few of the galaxies that have shown up. Again, they look really small and they're very, very red, so we think they could be distant galaxies, but we have to prove that, or we have to know something about the amount of dust, and we have to know something about the stellar population that's in them, whether they have blue or red stars. And so in addition to the imaging camera, which took these images, Hubble also has a spectrometer. That's a device that allows us to take the light and break it up into its individual colors of a little bit infrared, more infrared, mid-infrared, look at it in detail to see how the intensity of the light changes with the wavelength. And that's kind of like a DNA or a fingerprint. The detailed pattern, not just the smudgy fingerprint, but the detailed pattern of the swirls tells you more about the light. And in fact, the spectrum can allow us to test whether the lens model is correct, why the galaxy is red. Is it red because it just has only cool stars? Is it red because it has a lot of dust? And is it red because the galaxy is very distant? Of course, in many cases, it's all three of those. So we have to be able to disentangle one from the other. So the way they do that is Webb, JWST, takes an image and it finds some interesting objects. So here's one of the features that's seen in the infrared image. You can see these two streaks, and it takes the spectrometer and it looks at the two streaks and breaks the light up into different wavelengths of light. And what it sees is that this part is a little fainter and this part is a little brighter, as you can see here, but they have exactly the same pattern of the light, which means that these two streaks come from the same object in the background, And they are just images of that, distorted by the fact that the foreground lens isn't a nice, symmetric, perfectly cylindrical lens like we might expect it to be. It's a more complicated mass distribution. But this tells us that the two arcs are actually from the same galaxy in the background. And it allows us to measure exactly where those peaks take place, the peaks in the light. So here's a look at some of the objects that we were looking at before, and we can look at their spectrum again. So we take the light in the infrared, but rather than just making an image of it, we look to see how its intensity varies as you go from, say, 1 micron up to 10 microns across the infrared spectrum. You can see different patterns of the lines, and that tells you something about how much the shift of the light is. And so again, that tells us that the light left this galaxy 11.3 billion years ago, left this one 12.6, this one 13, and this one 13.1, a little bit more. And this feature is this feature, which is this feature, which is this feature. The features have been shifted, the light has been shifted to the red because the objects are further away. And so this is what Webb is doing now. And we haven't solved all the problems. We now know how to look for these very small reddish objects. And there are some simple ways, just looking at the images, the details of the images, that you can kind of imagine that we have candidates for distant galaxies, but no one object is guaranteed to be distant unless we can also measure the spectrum. So a lot of what's happening is now the first images are taken with the cameras, and then after people process the images, they go back and say, this galaxy looks really interesting, let's go take a spectrum. It takes longer to take a spectrum than it does to take an image, because in the spectrum, you're combining all the photons together to make the image. When you take a spectrum, you have to take the photons in this wavelength bin and this wavelength bin separately. And so you have to expose for a longer period of time. And so this is going to go on for another 10 or 20 years before we know all the answers, but we've already learned a few things that have already been surprising. We thought from Hubble that we kind of understood that the first galaxies formed something like 300 or 400 or 500 million years after the Big Bang. And we had the feeling that there wouldn't be that many further back, that it took some time for galaxies to form into these objects as the universe was expanding. But it turns out there are lots and lots of distant galaxies in the JWST images. This really wasn't expected, and it means that the first galaxies formed earlier than we thought they did. Most of our understanding of the early universe does not make this prediction, and so our understanding needs to be revised. Another thing that's interesting, and you can kind of see this, is that some of these objects have some structure. They're not just little blobs. Even though they're tiny because they're very far away, they actually show some structure. And the nearby galaxies, we saw spiral arms. Some of them were smooth, some of them had arms, some of them had bars in them. We were thinking that early galaxies would just be clumpy and lumpy and irregular and probably small, and that the structures developed later. But instead, we're seeing early galaxies that are already at those early epochs well formed. Another problem that confuses us is that it appears that galaxies that have supermassive black holes in their center, what we call active galactic nuclei, but these are black holes that have maybe billions of times the mass of the sun in them, huge black holes. They actually exist early on in the history of the universe. And we really don't understand how supermassive black holes can form early. Again, we think of black holes forming by the accretion of material, the gathering of material because of gravity into a small volume. And that's not supposed to happen really quickly in the early universe. So it also leads to the question, if these supermassive black holes existed so early, which formed first, the black hole or the galaxy? And frankly, we don't know the answer to that because we don't understand how these supermassive black holes could have formed. Another thing that we've discovered is that although most of the galaxies that we've been looking at that are candidates for distant galaxies probably don't contain that much dust, a lot of them do contain dust. Some of them are extremely dusty, so dusty that they don't show up in Hubble images at all, but they do show up in the JWST images. And that suggests to us that the galaxies are embedded in dust. Now, dust, we understand, is not like the stuff that I find on my table at home, which is embarrassing. It's rather silicon and carbon grains, which have molecules embedded on them. They're very cold. They exist in interstellar, in between the stars and galaxies. And in order to be made of carbon and silicon, you have to have carbon and silicon. I said at the beginning that the early universe, as far as we know, only was made of hydrogen and helium. So where did this carbon come from? So we don't really understand at all how the dust formed that early. And that kind of flies in the face of our understanding that life could not exist early on, life as we know it, because it doesn't contain any carbon. So I want to leave some time for questions for people. So I'm going to end here by just showing you this image again. And if people have questions about the image, we can talk about it. Again, these are foreground stars, but these little cutouts are blow-ups of what is seen in those tiny little boxes, and the light left those galaxies 13.7 billion years ago. So there's lots more that we'll hear about from JWST, and there's lots of other science that JWST is doing also. But let me stop there and see if there are questions.
Martha?
Yeah.
You mentioned that, trying to decide which ones to study further and to, to do the spectrum part on. Who makes that decision? And is there like lots of infighting?
No, we're much more civil than that. Okay, so every 6 or 9 months, I guess it's been longer now, but it'll probably be once a year or so, NASA puts out a call for proposals for the next year of observing with one of its telescopes like JWST. So in fact, the JWST proposals are due on Friday. And so there are astronomers all around the world who are madly trying to write justifications for why their favorite little galaxy in a box is worth following up with a spectrum, and not somebody else's favorite little galaxies that they found in the box. Remember, the images themselves have been made public, so everyone has access to them. And how you decide which one of these 10,000 galaxies you might want to spend an hour of time on with JWST, and you probably don't want to look at one, you probably want to look at 3 or 4, so it's 3 or 4 hours of JWST time. You have to justify it. And then proposals are submitted, and then a peer review committee is called together to judge the proposals. Now, last time, I don't remember the number, but there were probably 20 times as many proposals put in as there was telescope time available. So 1 out of 20 gets approval for telescope time. The reviewing is done by taking a few proposals and sending them to some group of people having each proposal read by maybe 6 or maybe 10 people. And then the average grade is looked at. And then a committee gets to decide which ones actually get telescope time. It's a very time-consuming activity, but it's believed to be the fairest way of giving out precious telescope time on these one-of-a-kind, very expensive resources.
Thank you.
I have a question on whether some of the things that you're seeing that are different or unexpected, whether they're giving rise to any speculation that in fact the date for the Big Bang may in fact be wrong.
Well, there are other clues that tell us better the date for the time of the Big Bang. Those come from other telescopes, in particular the cosmic microwave background telescopes, which are able to observe all the way back to about 300,000 years after the Big Bang. Now, it's also a very complicated problem, and I referred at the beginning to the fact that JWST will teach us about how the universe has expanded over time. And I didn't want to get into that because it's a completely different set of observations. It's going to take time to do that. And JWST will contribute to that, but it will also require other telescopes to do that kind of work, and it will take more time than this. So the current evidence point to this 13.8 billion years, but there are still things we don't understand about that, like why it is that number and not something else. We don't understand what causes the expansion of the universe, what causes the universe early on to slow its expansion, and then later to accelerate its expansion. And maybe that's a subject for another talk on another day, if somebody twists my arm.
Thanks.
Martha, if you had to characterize or draw a graph of really interesting new information, it sounds like from the get-go, there's tremendous amount of information. Do you see it as just a very high constant for a long time, as long as it's operating? I mean, this is just a wild guess, but it's probably an informed guess on the part.
Yeah, you can inform the guess by looking at other telescopes. You can look at what Hubble did. You know, people are using today to address different science questions, images that Hubble took 20 years ago.
Right.
People are, because all of the data are put into an archive, and people go back and they look at it. For one thing, one of my PhD students who finished 12 years ago did half of his PhD thesis going back to data taken with a very large array 10 years earlier, because and reprocessing it to make a new set of images, because our software and the algorithms to make images and the compute power that you had available was completely different than what you could do when the data were really taken. And so what you anticipate is that Hubble will make a whole bunch of big discoveries right at the beginning, because it's doing things that no one could do before. And then it might flatten off a little bit, and continue to produce lots of interesting results. But at the beginning, it's going to produce things that are one of a kind, the first of this, the first of that. And then people will start to do studies, surveys, where they observe groups of objects instead of just individual ones. And then it will find some new things that nobody had any idea existed at all. And people will go off in that direction, and there will be a whole bunch of new things. But what Hubble and Spitzer and the Very Large Array, and even going back to Arecibo, what all new telescopes have shown is that they continue to be productive, because they discover new things all the time that we didn't anticipate. JWST is is a little bit different from Hubble. Hubble was upgraded several times. They put on new cameras. JWST cannot be upgraded, but I anticipate that its data will be good for 40 years. And with some luck, it should take data for 20. And that's good because there's only one JWST, and it's taken a long time to build it and launch it.
Martha, does JWST only look in one direction, opposite the direction back to the sun?
No, it can actually look around. I'm not sure if this. It can look. It has this thing called. I have to. Yeah, you can see my screen, right? So it has this sun shield. Okay, and so it has to look opposite the direction to the sun, but it can point around, slew around to different parts of the sky. It can't look at some times of the year, it can't look in a certain direction because of the sun, but over the course of the year, it can observe the whole sky, and it can move itself around some within the sun shield. It's very complicated how it all works. It's also in this position that's opposite the sun's direction, and sitting out there, doing a little orbit around this gravitational balance point that we call L2 that we've mentioned before.
Right.
So scheduling the telescope is actually very complicated, and that, of course, is done by professional staff who are in charge of operating a telescope.
Thank you.
Hubble likewise can't observe all of the sky at any particular time, but it's in an orbit around the Earth, which makes it more complicated because not only can it look at the sun, it can't look at the Earth either. Controlling these telescopes is a non-trivial thing. Okay, well, that was really what I thought I wanted to update you all on today. And I will keep on top of JWST. And there are lots of other interesting things going on studying exoplanets. Maybe you've seen they're starting to take spectra of the atmospheres of planets around other stars. They're also able to actually take images looking for planets around other stars, which is very hard because the star is very bright and you're trying to look for a faint object around a bright one. That requires a different instrument than the normal camera. And so that's still in the checkout process, although they're starting to produce images. And of course, it also studies, it's able to peer into the dust and gas in regions of star formation. So there's just an awful lot of stuff going on, but everyone this week is writing proposals for the telescope time that starts next summer. And so there's probably no science being done this week. Everyone's writing proposals. All my young colleagues are writing proposals.
I know it. Martha, thank you for showing an infrared spectrum as someone who spent 10 years of her career in vibrational spectroscopy, using vibrational spectroscopy. It was de la Raman too, but it was fun to see a vibrational spectrum.
Yeah.
Infrared spectrum rather.
And it is exciting, but as you know, Anne, in fact, the infrared part of the spectrum is complicated because there are lots of molecules there, and there's dust which emits in the infrared. And so that's why this is really hard.
Yeah, we looked at pure samples. This is different.
Yeah, it's really hard. It's very hard to actually convince another astronomer that you've discovered a galaxy that exists at you're looking at viewed 100 million years after the Big Bang. So
That's
while I said that everyone is very civil and polite, there's tremendous competition between Group A located on campus X versus Group B located on campus W, as you can imagine. And then there's also competition between how much time are you going to spend on distant galaxies and how much time you're going to spend on looking for Earth-like planets. Which one is more important? But that's decided at a higher level. And of course, it also it depends on what people propose to do. If nobody proposes to look at distant galaxies, there won't be much time expended on distant galaxies. But astronomers learned 40, 50 years ago, 60, 70 years ago, that these telescopes, both on the ground and in space, are very expensive. And there's only one universe. And so if you want to do this, you really need to combine efforts. So collaboration is a very normal thing. And it's also true that a lot of the follow-up work for JWST can be done on the ground with big ground-based telescopes, which have a tendency to have different instrumentation, which will have newer instrumentation. And so we should also understand that JWST is great, but it doesn't exist by itself. It exists as part of a suite of powerful telescopes, many of which are supported by international consortia, where people work together in order to do science, because it's the science that drives them mainly. Okay, well, I'll think about something else in the future. If people have favorite topics, you can always pass them on to me.
Thank you.
Martha.
Thank you, Martha.
Bye-bye, everyone.
Bye.